All right, I'm going to explain how to do the simulation of restriction mapping activity. In order to do this, you're going to need this worksheet, and you're also going to need a ruler of some kind. Mine is a little girly ruler that's not very short, but as long as it's about 10 centimeters long, you're good to go. Worst comes to worst, you can print a ruler off the internet. Should be fine. All right, so the purpose of this activity is to be able to model the actual locations that a restriction enzyme cuts a plasmid. And the way that we do that is by running a gel electrophoresis, identifying fragment size, and then being able to map it on a plasmid. So if you haven't already read through this top portion, pause the video, read through it, and then come back. So what we're going to look at is restriction enzymes A, B, and C are cutting a plasmid, and when they were first run through gel electrophoresis, whether A, B, or C was run through, there was a circular plasmid that was 1,200 base pairs long, which indicates that they each cut at one time. So that if you have a circular plasmid, 1,200 was obviously very convenient because there are 12 hours on a clock, and so we can just kind of talk about the locations of cutting as hours of the clock. Of course, in real life, it won't be that simple. But whether it was cut, say, for example, here, if restriction enzyme was cut here, this entire thing would be 1,200 base pairs. So what scientists then did was ran restriction enzyme A and B, allowed it to digest or cut the plasmids, and then ran it through gel electrophoresis. And when both A and B were run, there were two fragments that came up at 300 and 900 base pairs. So say I established A cut at the 12 o'clock position, where would B have cut in order for two fragments to be made that were 300 and 900 base pairs? One option would be at this 3 o'clock mark, because then there would be two different fragments, of course, hundreds of thousands or millions of copies of each of these, because of course we know that they ran PCR first. So here we have 300 base pair fragment and a 900 base pair fragment, which allows us to start mapping the location of where the restriction enzymes are going to cut the plasmid. Now, why is this useful? If, for example, there was a gene that we wanted to insert into this plasmid, and we wanted to know where we were inserting it, that's going to be very important to know. Notice though that you can also cut it at the 9 o'clock position. Can you see this? Let's see. So if B was here, we would still end up with a 300 base pair fragment and a 900 base pair fragment. Okay, so before we fully map out the location of our three restriction enzyme cutting locations, we are going to model what the gel electrophoresis would have looked like that would have led to these results. So flip over to the back, and we're going to start by drawing our gel electrophoresis. So grab your ruler, start by drawing a line that's about 10 centimeters long by, I don't know, maybe about 12 centimeters long. It doesn't have to be perfect. That's 13. All right, the first thing we're going to do is we're going to draw the standard. Now the actual distance in centimeters and the number of base pairs are listed above. Remember that the standard is a control. This is a location that, or a DNA that has been digested with restriction enzymes that are known, and the resulting lengths of each of the fragments are known. So I guess before I can start running it, I'm going to need to draw in my wells. Now, we're going to do a total of 6 wells today that we're going to simulate if this was a gel electrophoresis, because we don't just run it all the way from the edge of the gel, right? The gel is inserted into these wells and allowed to run through the gel. Remember that DNA is negatively charged, and it's going to be attracted to the positive end when electric circuit is run through this gel. Okay, so here I just kind of sketched in my wells so that it's really clear that this is where the DNA is going to start. Then what I'm going to do is I'm going to use this list to lay out all these different distances. These are going to be the distances that our fragments are migrating to. So I'm going to set up my ruler. I'm going to put my 0 right at the far end of my well. Okay, and then I'm going to draw a line at each of those different distances. Now, the first 4 are going to be crazy packed together, so just be aware. You're going to have to be really, really careful. So here's 80 centimeters, 0.85. Sorry, I'm trying to get in here a little tighter, but there's a little iPad in the way here. 0.9, 1.0. 1.3, 1.6, 1.85, 2.35, 2.8, 3.5, 4.8, 7.0, and 8. Okay, so this is what our standard would look like as all of these different fragment sizes started to migrate away from the well down this gel. Now, each of these are a known size because they were cut with established restriction enzymes. So I'm going to start labeling them. I'm going to start from the bottom just because they're a little more spread out here. So this particular fragment is going to be consisting of only 17 base pairs, 30 base pairs, 100, 200. I guess I should label the top here DNA base pairs in fragment, I guess. Okay, now it's gonna get a little tricky here. So 300, 400, 500. I might have to start like labeling them. 600, 700. 800, oh, my pencil's getting a little dull. Switch her out. 900, 1000, and 1100. Okay, so now I have a known control that I can compare my next results to. So now we're going to indicate what would it have looked like if we had run DNA that had been cut by restriction enzyme A and restriction enzyme B. Now, if you flip your paper over, you'd remember that they were cut at the 300 and the 900 base pair. So, I'm going to use my ruler to try to be a little more exact here. So there's going to be a line at 300 and at 900. Okay, so this is what scientists would have looked at in order to get this data. So the whole reason that we can draw this map is thanks to this gel electrophoresis and being able to compare the fragment size to a known standard. Pretty cool, huh? So what would it have looked like if we used both B and C enzyme and A and C? So if you're watching along, please pause the video, go ahead and draw those in, make sure you understand, and then come back to me. 1100, 100, about there. 800, 400. Ooh, not beautiful, but okay. So hopefully yours agree with mine. Let's keep going. So now, how can we map those restriction enzymes? So we already established that if A was here and B was here, we'd be able to have a 300 and a 900 base pair fragments that we are seeing here. Now, based on this second result, the distance between, or when B and C both cut the fragment, we're going to have a 100 and an 1100 base pair. So say B was here, C would therefore be able to be where in order to have, so say A is not cutting it, but just we added B and C, and we had a 100 and an 1100, where could C be? Okay, we've thought about it, pause it maybe. So C, you kind of have two options. It could either be at the 2 o'clock mark or at the 4 o'clock mark. If C was here, you'd be able to have a 100 and 1100, Or if C was here, you'd be able to have 100 and 1100. So we kind of have two possibilities for C, but when we look at our third set of data, only one of these two is going to work. So the third one says when we cut with A and C, so say now that B is not being cut this third time, we're going to have a 400 and an 800 base pair. So if C was here, then you would have 200 and 1,000. So that's not going to work. But look at this. If C was here, you'd have 400 and an 800, which is exactly what we got on the other side. And so we can erase this one because we now know by looking at all three pieces of data that this must be the location of where those restriction enzymes are. Or alternately, like we talked about on the other side, they could be the other way. So A, B, and then C would be at 8 o'clock. Okay, the last thing is we're going to say, well, how would our gel electrophoresis look if we had restriction enzyme A cutting in two locations? So you can choose any location you want for the second site of A, and then you're going to just sketch here what would happen and what would the gel electrophoresis look like. So I'll do one for you. Let's say, I don't know, 10 o'clock. Okay, so say that A cuts at the 10 o'clock and at 12 o'clock. So now, if we run restriction enzyme A, we're going to end up with 1, 2, 3, 4 different size fragments. So I'm going to put a little star here to indicate this is if A basically has two cuts. So this is just an extension activity. This is number 4 if you're following along on the front page. So say that we use this restriction enzyme A star that then cuts in two locations. What would the gel electrophoresis look like? All right, so I realized that I just made a mistake and I had to go back and erase it. So what I actually did, that I'm hopefully gonna just edit out, is I had all three of these restriction enzymes digest this DNA, this plasmid, and so then we ended up with 4 fragments, but we're just doing restriction enzyme A that cuts twice and B. So we're gonna pretend that C is not cutting and we're gonna say what size would the fragments be? So this one is gonna be 200 base pairs, this one is 300 base pairs, and so this one is going to be 700 base pairs. So then over here, we're gonna come up and we're going to just map those on the gel and what they would look like. So there would be a 200, a 300, and a 700. Okay, so now what I'd like you to do is the final one, where say that we were doing this new restriction enzyme, this little extension where there's 2 cuts, but say there was no B, now it was just cut with A and C. And we could keep going and get extra practice and say, well, what if we used all 3 of them to cut A, B, and C? What would it look like? So the idea here is just so you get some practice with gel electrophoresis and understand how we can use gel electrophoresis to understand fragment size and then be able to map the location of where restriction enzymes cut the DNA in a plasmid. All right, hope that's clear, and good luck.